An axpy operation is short for ax plus y. I've also heard this called a saxby operation, scalar a times vector x plus vector y. So axpy means ax plus y. Those operations begin with three variables. One is alpha in the real number, so that's a scalar variable. Then we have two vectors, x and y, which are m by 1 column vectors with m rows and 1 column. We define the axpy operation, alpha x plus y, as alpha times x, so that's a scalar vector multiplication. And then once that operation is completed, we do a vector-vector addition. So alpha x plus y. Each individual entry, so if I look at the ith entry, it's going to be alpha times the ith entry of x plus the corresponding ith entry of the vector y. Over here, we see some pseudocode to achieve this mathematical operation in MATLAB syntax. So this pseudocode says for I goes from 1 to m, set the ith entry of a vector w. So in this case, we're saying w equals alpha x plus y, axpy. So wi is equal to yi plus alpha times xi. And we do that for each I goes from 1 to all the way to m. So this is the pseudocode to achieve this operation. Just like we've done in the past, let's go ahead and start a new script file. We'll go ahead and save as. And this is going to be axpy operation algorithm. So axpy operation. Remember, axpy is ax plus y algorithm. So this is just a fast one. And then what we're going to need to do, of course, we actually need 3 different vectors and 1 scalar. So let's set alpha equal to 8. Feels really good. We'll set x equal to, this one's kind of interesting. Maybe we say 1's. Of course, we're going to need a dimension. So this is going to be a column vector. We've been kind of focused on that. Let's do a 4 by 1 this time. So here we'll say m comma 1. And then y, perhaps we say, is rand I, so random integer, and we'll go to 10. So this is some vector. Let's recall real quick. That fills the vector with random integers between 1 and 10, and it will be of size m by 1. So for some reason, oh, of course, let me rerun that. Yeah, there we go. My m was already in the workspace from a different MATLAB thing that I was doing. So here I've reset m to be 4, and of course y is a 4 by 1, which is what we expect. All right, so here we're gonna create the axpy operation. Let's do the one that MATLAB would do first. So MATLAB, I'm gonna take alpha times x plus y. So this is MATLAB code that produces the axpy operation. And then what we wanna do is implement an algorithm where we overwrite previous values of w with new values of w. Here we're going to initialize, so initialize w to be all zeros. Initialize would be all zeros. Output. Notice this is not very well documented code. This is the difference between Sandbox code and code used for other people. So I'm using this code literally just to get my head around what's going on here. I'm not using this as something that I'll somehow refer to other folks. So I call this Sandbox because I'm just playing in the sandbox. I'm not constructing a building, right? Those are different types of engineering. Okay, so for I goes from 1 to m, we're going to set the ith entry of w to be equal to, and this one I'm going to call out multiple times. So we'll reference the ith entry of y and add that to alpha times the ith entry of x. Okay? Claim, once I've implemented this code, the w that we produce through this for loop should be identical to this w, and we'll do that. Let's verify output. So one of the really cool things about programming is that we have to actually check that what we've done satisfies what we want. So there's kind of 2 ways to do this. We could actually put both of the vectors next to each other. So that's one way to do that. Let's run. And it is upset because I didn't put an S on the zeros. That's very nice, thank you. So we noticed that the output that MATLAB produced via this line of code that's that first column, is identical to the output that we produce in our for loop, and that's that second column. So in other words, this algorithm actually does what we expected, and we've compared that algorithm against MATLAB's internal version of this, and they're identical. Another way to check that they're identical is actually to take the difference between them. So if we look at wmat minus w, and then run, notice that that's 0. We say that the difference between two vectors is 0 if and only if both vectors are identical to each other. So that's another way to kind of verify that that works. Y'all know my steez. Once I code something up, I want to be able to visualize something. This gets into a large theme of mine in math and STEM, which is looking for multiple representations of the same idea. I spend a lot of time talking about verbal, visual representations, symbolic representations, pseudocode. This is something that I think is a tribute to deep learners. I find that when we have many, many different ways to encode the same idea, the mental model that we have is more robust and stronger in that way. And so from that standpoint, over on the left-hand side is the syntax to implement this, and over on the right-hand side is this visual that we've been developing. So we have kind of 3 different ways to think about this in this visual. So we have the math equation. We set w equal to alpha x plus y. So this is an axpy operation. The pseudocode implementation of this is for I goes from 1 to m, assuming, of course, these are m by 1 vectors. We set w sub I to get y sub I plus alpha x sub I. We do that I times. And then the visual progression that we have in this algorithm that we just did, we've initialized w to be 0. We have x sitting in memory, and we have y sitting in memory. Both were 4 by 1 because of our choice of dimension. We also have this alpha sitting in memory. And then what we do after initialization, we're going to overwrite each of these zeros with alpha times the corresponding entry of x plus the corresponding entry of y. So let's do that. When we kick into iteration 1, the first entry of w, we overwrite with y1 plus alpha x1. We go to iteration 2, y2 plus alpha x2, y3 plus alpha x3 in the third iteration, all the way down to the last iteration, which is write the value of m. Last value gets y4 plus alpha x4. Then we kick out, and we have not changed the values of alpha, x, and y in memory. We have only created a new vector that stores the axpy operation between alpha, x, and y. One of my favorite parts about numerical linear algebra, so implementing linear algebra on computers, is that we can't stay theoretic. It has to be put on the ground. I like to call this strategic deep learning. Strategic means practical strategic thinking, on the ground, real life constraints. Deep means very deep understanding of the material, and then learning means changing our brain to update our model of the world. This specific implementation doesn't care about memory costs. So when I define a new vector w to be y plus alpha times x, I can store as much memory as I want with no cost. But in reality, our machines that we're running on actually have a cost associated with memory. Our memories are not infinite. And so one of the things that we're going to see over and over and over again in the introductory level that we're at, we will literally just talk about a memory saving technique. But this is a theme in numerical linear algebra, writing code that takes into consideration the way that our machines are designed and the constraints within the machine in a very strategic way to still achieve the mathematical result, but do it in a smart way. So here, this first no memory saving algorithm for an axpy literally has a third vector of the size of x and y. So we're taking almost 50% more memory than just x and y, right? So imagine these are 1,000 by 1 vectors. So 1,000 by 1, 1,000 by 1, that's 3,000 separate entries we're having to store, whereas the data itself is in 2,000 separate entries. So we're 150% of what we need. The memory technique here is actually to overwrite y with the new value, meaning that the total amount of memory, if we think about this, is going to be 1,000 entries in y, 1,000 entries in x, and then 1 scalar, so that's 2001. Here, we only need 2001 entries. Here, we would need 3001 entries because I'm actually creating a new vector to sit in memory, and that's quite expensive. I mean, that, you know, if these were million by ones, you might actually break your machine, which might be a fun thing to do to kind of see what's going on. But our machines have finite memory. So the major idea in this memory operation saving algorithm is, instead of creating a new vector w equals alpha x plus y, what we'll do is we will take the vector y that's stored in memory and overwrite all of its values with the individual axpy operation. So this one down here, we call this a memory saving technique. It's not a mathematical idea. This departs from mathematics, right? This is not theoretical. This is practical. What we're going to do is overwrite each value of y with the individual axpy operation, which means when we go over here, we no longer need a new vector in memory. And then what we're going to do is overwrite each new value of y with y plus alpha xi for each individual loop. And then what we're going to do is compare the output of our axpy with this value. Notice it's the same thing. This algorithm produces the exact same thing. It's just where we're stored in memory. This is going to be particularly useful later. And then if you all decide to really get excited about this stuff, there's a really, really rich history of how to implement linear algebraic operations on machines in optimal ways. With that, I pose 2 community challenges to you all. Community challenge number 1, how would this code differ if we were looking at axpy operations between row vectors? Here we've done an axpy operation on column vectors. What would you do if it was a row vector? Can you change the mathematical definition and then also both of the pieces of pseudocode here? And then the second one is, can you visualize what's happening with the memory operation in the same way that we visualized this, right? So we have this progression where we were overriding the new vector with the axpy operation from the old vector. What would change in memory? So remember, this is kind of a visual progression of what's happening inside the computer memories. How would this visual representation change if we use our kind of memory saving, where we're overriding y with its corresponding axpy operation? So what would change in this visual? All right, y'all, thank you so much for your attention, and we will continue exploring if statements in the next video.